All right, so now we're going to jump into something called Ksp, which is related to our other Ks, but very different. So Ksp has to do with precipitation reactions. Okay, so we talked about precipitation reactions last unit. They would be something that forms a solid, which I've labeled here as precipitate, PPT. So this would be the overall reaction, and then down here would be the net ionic equation. So what we talked about last unit when we did this is we said that we wouldn't worry about any leftover ions that, like, I remember saying that they were negligible, that we would eventually learn how to figure out how much there was, but for those ion problems, we just said we'll just ignore the fact that there might be some ions dissolving from the precipitate. So this is the type of problem that we were looking at. So this is the type of problem that you would have seen on your Unit 1 test. So here, I'm going to go over this problem now just as some practice. But if you want to pause the video and try it on your own, you should be able to do this entire problem. It's exactly what was on your Unit 1 test. So this would be a great way to review before we get into the new stuff. So what I'm going to do first is write the overall equation and then write that as a net ionic equation. So the overall equation here would be, oops, zinc nitrate plus sodium hydroxide gives us zinc hydroxide plus sodium nitrate. And to balance that, we can do this. Now the net ionic equation would be, we would break up everything except our precipitate. Our precipitate is going to be this right here. So we would break everything up and we would end up with Zn, and then cancel out our spectator ions. And that would be our net ionic equation. Okay, so the next part of this would be to ask which ions remain in solution after precipitation, order them from highest concentration to least concentration. So first we need to figure out what the limiting reagent is here. So for our zinc nitrate, we take our 0.1 liters times the molarity, and we get this many moles. We divide by the coefficient for limiting reagent, but here our coefficient for zinc nitrate is 1, so we can leave that alone. Then we're going to do NaOH, which we do our 0.1 liters times our molarity, gives us this many moles. We divide by the coefficient, and we get this. So that means NaOH is our limiting reagent. So what we would assume there is if we go back to our reaction and we're figuring out the ions left in solution, if this is the limiting reagent, we say there's none here, we're going to have For our excess, well, we would have used 0.002 of this, so we'll have 0.001 left. Precipitate we don't care about for ions. And then we're going to make 0.002 here. Oh, excuse me. I was doubling the wrong thing. So we would do 0.004. Okay, so that's how much we would have there. And then for our ions, we're going to say that OH was completely used up because it was in the precipitate. Okay, so that's what we would have said last unit. So we would just be looking at Zn2 plus and NO3 minus and Na plus. So for Zn2 plus, we have 0.001 left over. Okay, and that's all we're going to look at because our zinc hydroxide here took the rest of it. So we have 0.001 moles. And then for our nitrate, we have the 0.001 that's left over here times 2. Okay, because we would have 2 nitrates for every one zinc nitrate. So we would do 0.001, that's in excess, times 2. And then we would add that over here to the 0.004. Okay, we don't need to worry about the coefficient there. So 0.004 moles gives us 0.006 moles of nitrate. And then Na plus, we just have to use the 0.004. Okay, because this Na plus is all gone, so all we have to worry about is this one. And so that's going to be 0.004 moles. And then the question asks us to order them from least to highest concentration. Okay, so here you wouldn't have to divide by the liters because obviously you're going to divide by the liters for each one of them. So if you put them in, you can just do it here and we'll do the liters in just a second. So from lowest to highest, we would do Zn2 plus and then Na plus and then NO3 minus. And then the next one says to find the mass of precipitate, so the mass that of our zinc hydroxide that was formed. So all we have to do there is take our moles of limiting reagent. And I'm just going to use OH minus. We can just use the net ionic equation, gives us a little bit better math if we just use this. So we can just use the 2 OH minus and then this for the precipitate. So we have our mole ratio here. Our molar mass of zinc hydroxide. So that gives us our mass of precipitate that would form, or in theory would form. That's actually our theoretical yield, but that's not this problem. All right, so the last one is to find the molarity of each concentration, of each ion. Very easy. All you have to do is take your moles and divide by the volume. So here we have 0.001 moles, and then the volume we would assume would be additive. So we add these two together, and we're going to get 0.2 liters for all of them. So we're going to take this, divide by 0.2, and that's going to give us this for Zn2 plus. And then what was our next one? NO3 minus. We take our 0.006 moles, divide by 0.2. And the last one, our Na plus. Oops, 4. So those are our concentrations. So that is the type of problem you would have seen in Unit 1. There were also very similar problems on your Unit 1 test. So this should be very familiar. I wanted to review that because now we're going to kind of turn it on its head a little bit. If you were to get a question like this on the AP exam or on any other type of exam, you would not have to do anything that we're about to do. If you have to do KSP, it will be very specific that you have to do it. Okay. So here we get into the next part of this. So the real truth is that precipitate is not as solid as we have been assuming up until this point. What will happen is that a little tiny bit of it will dissolve, and there will be an equilibrium between that, okay? So this one is our net ionic equation that we just looked at. But again, there is more to the story here. Some of this precipitate will dissolve. It's going to be very small amounts, but some will dissolve. So this reaction will be able to go in the reverse direction as well. So a more accurate version of this net ionic equation is this one, where we have an equilibrium arrow. Okay, now again, this isn't something that they were expecting you to do in the last one. If it's a KSP problem, they will be very specific about it. But now we have an equilibrium thing, so we can specifically write our equilibrium constant. So this is what we would write for K. Now there's a 1 on top because this is a solid, right? And we don't write solids in our Ksp expressions. Okay, so that's why there's no concentration of zinc hydroxide, because we wouldn't write that. Okay, so instead we would put a 1 up there, and then the concentration of the ions would be on the bottom. Okay, so that's where K would come from. However, that is very kind of super annoying because it's always 1 over something. So instead, we decided that we were going to flip the reaction. Okay, because if we flip the reaction, we take the reciprocal of K. Remember that from the last couple videos ago. So if we flip the reaction, we take the reciprocal of K. We call that Ksp. Okay, so our Ksp would just be the 2 ions, just like you would expect. And if you wanted to write them over 1 just to show that you have a solid on the reactant side, you can do that, but that seems kind of silly. So Ksp would just be this. Okay, we write Ksp and not Kc because we changed the reaction. We flipped it. So what this is now saying is, okay, if my old reaction made this much solid from my precipitate, I know that a little bit dissolves, so I'd have an equilibrium with the ions precipitating out. Okay, so that's what our Ksp is going to be. So let's delve a little bit into Ksp. So let's see. Here, 6 grams of calcium hydroxide was placed in 3.5 liters of water, but it did not all dissolve. Here's our equilibrium expression. Well, equilibrium equation, excuse me. Equilibrium expression would be Ksp here, because we have our solid breaking up into its 2 ions. So we would have Ca2 plus times OH minus concentration squared. Okay, and this is concentration Ksp, so you do need those square brackets. If you knew that this saturated solution just means as much as can be dissolved is dissolved. The concentration of dissolved calcium hydroxide is 0.0117 molar. Calculate the Ksp. Okay? So what we need to do is find the concentration of Ca2 plus, the concentration of OH minus, and plug them in here. All right, our calcium hydroxide that's our formula for calcium hydroxide. So we know that the concentration of Ca is going to be equal to the concentration of calcium hydroxide because for every 1 mole of calcium hydroxide, we get 1 mole of calcium, so Ca2 plus. So that's going to be our molarity. So that's going to be the same concentration. Now for OH minus, we're going to do 2 times the concentration of calcium hydroxide. And that's because for every 1 mole of calcium hydroxide, we get 2 OHs. So we're going to do 2 times. And we get that. All right, so now all you have to do is plug in your 2 concentrations into your Ksp. So Ksp is equal to so it will look like that. And just like our other Ks, there are no units on this K either. All right, so let's go over some words, vocabulary that we're going to be using. As long as there's some solid on the bottom of our beaker or whatever, we can be sure that there is an equilibrium and that the solution is saturated. So saturated just means however much can be dissolved is dissolved. So we assume that if there's some on the bottom, as much as can be dissolved is dissolved. That's really important because then that means equilibrium is reached and we can use the Ksp number. Okay, so the rate of dissolution and the rate of crystallization or forming the solid would be equal, just like when we talked about the other equilibriums, the rates are equal. Solubility, which we're going to be using quite a bit on this topic. The maximum amount of solute that dissolves in a fixed quantity of a given amount of solute at the given temperature. Okay, so you can have either molar solubility, moles per liter, of the solid that is dissolved, or gram solubility, grams per liter, of the solid that does dissolve. Okay, so when you see I wrote that both times. that means that we're looking at the amount that dissolved. So when we ask like what the molar solubility is or the gram solubility, we're asking how much is dissolved in a saturated solution. So these are the types of questions that we will be going over in the KSP topic. Okay, we already did the first type of question. We're going to do a couple more of those. We're also going to be able to talk about molar solubility and, quite frankly, gram solubility. We can do them both here because you can just convert moles to grams to figure out the gram solubility. So those are the ones that we're going to focus on today. Next video, we'll be looking at common ion stuff. Okay, don't worry about that for now. And then later on, we'll talk about does a precipitate form, and then we'll do it's a Q, like you did last time where you found Q, and then you can compare it to KSP and all that. Okay, so we will do those types of questions later on. In this video, we're just doing the first two types. All right, so let's take a look at another problem where we're looking for and finding KSP. So like that first type of question, okay? Lead 2 sulfate has a solubility at 25 degrees Celsius of 4.25 times 10 to the negative 3 grams per 100 milliliters. What is the KSP? And then they give us the molar mass of our lead 2 sulfate so that we don't have to worry about calculating that. So first thing I'm going to do is write the KSP equation. So I would write my precipitate and then my two ions. And this is balanced as is. So now my Ksp expression for this would be the concentration of lead 2 plus times the concentration of sulfate. So now what we need to do is find out the molarity of these two things. It's like we did in the last problem, except this time we're not given the molarity of the solution. We're given the gram solubility of the solution. So what you can do is figure out how many moles, then divide by the 0.1 liters that we have up here. And then that will give you your molarity. Okay, so what we're doing is assuming 100 ml solution. So we take our gram solubility, and that's grams of our precipitate, and we're going to convert that to moles of our precipitate. Okay, so that's our moles. Now to find the molarity, we just divide by 0.1 because they said it's grams per 100 milliliters. So that gives us, this of PbSO4. Now what's nice is this molarity is also the molarity of our lead 2 plus and our sulfate because all the coefficients in our balanced equation are 1. So if the ratio is 1, then the molarity is the same for all of them. Okay, so all we have to do is plug this into our Ksp expression for lead and sulfate. And then that gives us this. Okay, I wanted to give one more type of question like this before we moved on to the other type of question. So if you would like to pause the video and try this one on your own, it's very similar to the one we just did. The main difference being that this gram solubility is given to us grams per liter. So you don't have to divide by that 0.1 because it's not 100 mils here. So for this one, we have lead 2 fluoride. That is not balanced, so we need to put a 2 right here. So it does change our Ksp expression slightly. So now our Ksp is going to be the lead 2 ion, F minus ion squared. So we're going to do the same thing that we did before, where we convert our grams to moles of PbF2, then we'll have the molarity, and we can use that in our expression. So we're going to take our 0.64 grams divide that by the molar mass. We get this for our moles, but since it's per 1 liter, we also know that's our molarity. So now our molarity of Pb2 plus is going to be exactly that. Okay, so your molarity of Pb2 plus is equal to this because for every 1 mole of PbF2, you get 1 mole of lead because the coefficient is 1 on lead. However, our concentration of F minus is 2 times the concentration of PbF2 because for every 1 mole of PbF2, you get 2 F minuses. So that's going to be 2 times 2.61 times 10 to the negative 3, which comes out to this. Now I can go ahead and plug these concentrations right into my Ksp expression. And don't forget about that squared. We use the 2 kind of twice here, okay? We use the 2 to multiply by the concentration, and then we also square it. One does not take care of the other. So here is our Ksp. Okay, one last one just like this one, where you're just finding Ksp in given solution. This one is nice because it gives you the concentration. You don't have to worry about converting to grams. Converting from grams to moles. We already have the concentration. When you're given the molar solubility, it's a little bit easier. I highly recommend stopping the video here and trying this one on your own, and then coming back for the explanation. So we have silver phosphate. And silver is one of the ions that you need to know. It's the transition that you need to know is just +1. You need to know silver is +1 and zinc is +2. And then we get this for our Ksp reaction. So our Ksp expression looks like that. So our concentration of Ag plus equals 3 times our concentration of the precipitate. So Ag3PO4, you need to do 3 times that. So that comes out to be 4.8 times 10 to the negative 5 for our concentration of Ag plus. Our concentration of PO4 minus is just the same. We don't have to do anything because the precipitate and PO4 minus have a 1-to-1 ratio. And then you just plug them in into your Ksp expression. We have 4.8 times 10 to the negative 5 to the third power. And then we multiply that by this, and we get 1.8 times 10 to the negative 18. You can see this Ksp is very small, negative 18. That just means not a lot of this is going to dissolve. Now we're going to go the other way around. So this is the second type of problem that I had on that list of problems. And these are the 2 types of problems we're going to do in this video. So now you're given the Ksp and you have to calculate the solubility. This question wants both molar and gram. Once you find one, it's really easy to find the other. So what I'm going to do is write my equilibrium expression for calcium carbonate. And write my Ksp expression. And we know that it is equal to 4.5 times 10 to the negative 9. So here we're going to start using Rice tables again. Okay, so we have our reaction, our initial, our change, and our equilibrium. So we're going to want our equilibrium concentrations for Ca2 plus and CO3 minus. We do not really care about the precipitate, right? Because we're looking for solubility, which means we need to find concentration, which means we need to use Ksp. So here, it doesn't really matter what you put. You can still include it. So you can just write we have some, and we are going to lose some of it, but we have none of this to start. So our initial is that we have some amount of calcium carbonate, and it does not matter how much, so let's not try to worry about that. We're now going to use S as our solubility. Okay, so S is going to be stand for solubility. That's going to be our change. We're going to make S be the amount that dissolves. So if S dissolves, that means we subtract S here because it's not going to be solid anymore. And then it's going to turn into S here. Okay, we're going to add S. So here you can just write less, or you can write some minus S. It really doesn't matter what you put there. Here, you would have the 2 S's. This is what we want for our Ksp. Okay? So now we can plug in S into our Ksp expression. So Ksp is going to be S for our Ca2 plus times S for our CO3 2 minus. So Ksp is going to be S squared. We can set that equal to the number that we know and solve for S. So our solubility is going to be the square root of 4.5 times 10 to the negative 9. So that's our solubility. So the molar solubility is this. Okay, and you know that because I put a capital M after it. To find the gram solubility, you just do what we did last time. Okay, you just take that, and remember molar solubility is moles per liter. So I'm just going to write our molar solubility as moles per 1 liter. And I'm going to multiply that by the molar mass, which is given to us in the problem. And moles will cancel, we'll end up with just grams per liter. Okay, because we didn't do anything with the grams and the liters. So that is our gram solubility. Nice and easy. So let's try another one, very similar to that. So we'll start with our solubility expression. That gives us our Ksp. Which we know is equal to this. So now we set up our rice table. We're going to have some of our precipitate, but none of our ions. Our change is going to be minus S here. Here's where this one differs a little bit. Okay, now in our reaction, we have a 1-to-1 ratio for BaF2 and Ba2 plus. So our change there is still going to be plus S. But we have a 2-to-1 ratio between F minus and BaF2. So our change, remember back from when we first started rice tables, our change is not going to be S here. It's going to be plus 2S. Because for every one BaF2 that breaks up, you get 2 F minuses. Okay, so we're going to have less here, doesn't matter, S and 2S here. So instead of just plugging in S's into our Ksp expression, we're going to use S for Ba2 plus, and then 2S for F minus, and then of course that is squared. So when you do that out, you get 4S cubed is equal to your Ksp. S3 set to 1.7 times 10 to the negative 6. Yep, sorry, messed up. You can solve for your solubility, and you get 7.5 times 10 to the negative 3. And that's going to be your molar solubility. And then to find your gram solubility, you just take that number, just like we did for the last one. It's going to be moles of our barium fluoride over 1. Put your molar mass, whoops, and you would get 1.3 grams per liter for your gram solubility. All right. So what I would do here if I was you is pause the video and try this one on your own. It's very similar to the last one we did, but it's only asking for molar solubility, and then it asks for the concentrations of the two ions. Okay, so you should be able to figure that out. You can go ahead and try it and then come back here. So the first thing you should do is write your equilibrium expression. And your Ksp. So now we can use our Rice tables. We're going to subtract S here, add S here, and then add 2S here. Again, because every time you dissolve or dissociate one of your CaF2s, you get 2 F minuses, so the change will be double. So then we have S and 2S. So we can go ahead and plug that into our Ksp. We have S for calcium, 2S squared for fluoride. So 4S cubed is equal to our Ksp. And then when we solve for S, our molar solubility is 2.1 times 10 to the negative 4. So now it asks us to find the concentration of Ca2 plus and the concentration of F minus. The concentration of Ca2 plus is equal to the solubility of CaF2. Okay, so if the solubility of CaF2 is this, then so is calcium because they have a 1-to-1 ratio. So we have 2.1 times 10 to the negative 4. And then fluorine will be 2 times that. And that's it. Those are those two types of problems.